Hello again. So in the second part on this derivation of the Navier-Stokes equation, we established that the transient term here in the equation of motion on the left-hand side of that equation can be combined with the convective term, and we're going to obtain the substantial time derivative of the velocity, which is a circle here in green. So now what we want to do next in that last part, we want to use the basic generalization of the Newton's law of viscosity. Okay, so remember we discussed that in a different classes, but we obtain for tau, like the viscous stress tensor, we wrote it as tau equals to negative mu, the viscosity, times nabla applied to the velocity vector, plus the transpose of that matrix. And plus 2/3 of mu minus kappa, where kappa was the dilatational viscosity, times the dot product of that nabla operator and the velocity, so that means basically the divergence of the velocity, and don't forget to multiply that by the identity matrix. Okay, so the result basically is a matrix. I think that's also something that we established. And so if you are inputting basically this tau right here in the equation of motion, then basically you get the Navier-Stokes equation. But what we're going to do now is we're going to simplify this a little bit further and consider that we have an incompressible Newtonian fluid with constant viscosity. Okay, so let's write there. So case of an incompressible Newtonian fluid with constant viscosity. So first of all, if you have an incompressible fluid, then you know that the divergence of the velocity is going to be 0, which means that your viscous stress tensor simplifies to tau equals to the negative of mu nabla u plus the transpose of that matrix. Okay, great. So now we're going to rewrite, in the equation of motion, or now in the Navier-Stokes equation, what we have is actually the dot product of that nabla operator and the viscous stress tensor. So we are going to try to look at it in more details. So first, let's check one of these components. Let's say the ice component. Okay, so we look at one component I. So how do we write that component? Basically, this will be written this way, since this is we apply that nabla operator, so that's basically going to be written as the sum over j of the partial derivative of tau ij with respect to xj. Okay, so you can also further distribute that. So that's the partial derivative with respect to xj of what? Of what we have highlighted right here, of negative mu. And so the first term here in that remaining the viscous stress tensor would be written as the partial derivative of ui with respect to xj, and here we have the transpose, so that's going to give us the partial derivative of uj with respect to xi. Okay. And we're going to transform a little bit further that expression. So let's do it, okay, here. So that's going to give us the sum over j of what? Of negative of the viscosity. So here we have the partial derivative with respect to xj, which is applied twice. It's going to give us d2ui over d2xj, so dxj2, sorry, minus viscosity times d2uj, and then we have partial derivative xj and partial derivative xi. All right. Okay, and next, and we are going to rewrite it as negative mu d2 ui partial derivative xj2 minus mu. And what I'm going to do here is exchange the roles of xi and xj. So I will put xi first and then xj here. Well, that's okay if the transformation here is fine if you assume that the order of differentiation basically can be exchanged. Differentiation can be exchanged. So that would be if you give a kind of mathematical explanation, and that would mean actually that your velocity field is sufficiently smooth. Which means that the second order derivatives are continuous. So that gives us this. That gives us the sum over j of the negative of the viscosity, and here we have the second order partial derivative of ui with respect to j minus mu, and partial derivative with respect to xi of partial derivative of uj with respect to xj. Okay. So you might wonder how it would look like if we were actually writing the actual components of the velocity and of the stress tensor. So let's take an example. Let's fix I. Let's say it's equals to x, okay, because I and j both variables can be 1, 2, or 3. So in the Cartesian coordinate system, it's going to be x, y, or z. So here I is fixed because we were looking at the i's component actually of that tensor, and j is going to be either x, y, or z. That means that if we get back to what we were writing a little bit earlier, this is simply going to be written as negative of mu. So here we first going to have the second order derivative of velocity ux with respect to each spatial coordinate. That's going to be d2ux with respect to x2, and then d2ux derived with respect to y2, and finally the second order derivative of ux over dz2. So that's for the first part. This corresponds, remember, to minus mu times, the sum of negative mu and d2ui over dxj, the sum over j. And we have the second part, which is going to be negative mu, and here we have first d over dx of dux over dx plus d over dx, because again I is fixed, of duy over dx, and plus, I will write it here because I'm lacking of space, d over dx of d, oops, sorry, I made a little mistake here, it was duy over dy, and finally plus d over dx of d uz over dz. Okay. So you probably recognize again that we have the divergence of the velocity, which is going to appear in the second term, and that second term corresponded, by the way, to the sum, that's the sum over j, right, of negative mu d over dx I, so in this case xi will be just x, du j over dxj. Okay. So next, what we have is negative mu dux over dx square plus d2ux over dy square plus d2ux over dz square. And now we have negative mu d over dx of dux over dx plus du y over dy plus du uz over dz. And this term here is nothing but the divergence of the velocity. Okay, and you know that you have a incompressible fluid, because that's our initial assumption. Compressible fluid means divergence of the velocity equals to 0. So your term here, your component of the derivative of the viscous stress is going to give you negative mu d2ux over dx squared plus d2 ux over dy squared and plus d2 ux over dz squared. That's the only surviving term. So in other words, what we've just demonstrated is that the sum over j of partial derivative of tau ij over xj with respect to xj is just sum over j of negative mu, the second order derivative of ui with respect to xj. Okay, and again, I will write that again, although we've said that many times, it's for incompressible fluid. And so, more generally, what we've demonstrated is that our dot product of that Nabla operator and viscous stress tensor is just negative mu times the second order derivative with respect to the position of the velocity, which we call also the Laplacian of the velocity. So finally, we can input that results in our equation, and we get rho times the substantial derivative of the velocity equals to negative Nabla operator applied to p plus mu Laplacian of the velocity and plus rho j. And that is the equation that we were looking for. The Navier-Stokes equation for an incompressible Newtonian fluid with constant viscosity. And that's it. Thanks.